Good morning. I'm Dr. E. Kavita, working as Assistant Professor in the Department of Chemical Engineering, SRM Institute of Science and Technology. I welcome you all for the video lecture on cleaner technologies and sustainability. And this is Module 3, Part 2, which comprises about hydrogen production methods, fuel cell, basic principles involved in the clean fuels. What are the various sources of clean fuels? So let us move on to the video. Hydrogen production. Hydrogen is considered a clean fuel as it produces only water vapor during combustion. However, production methods may vary significantly based on their environmental impact. And there are various methods of hydrogen production. They are steam methane reforming, partial oxidation, water electrolysis, direct thermal or catalytic water splitting. So one by one in brief, let us discuss. So the hydrogen production methods that combines the traditionally available industrial processes and also emerging green technologies to produce the clean fuel. So steam methane reforming, one of the methods of production of hydrogen. Steam methane reforming, the most widely used method for industrial hydrogen production, primarily from natural gas, and it is a thermochemical process. So the process involves the reaction between methane and steam at high temperatures around 700 to 1000 degrees Celsius and pressure 3 to 25 bar over a nickel based catalyst. And the main reaction is methane with water to produce carbon monoxide and hydrogen, and it is an exothermic reaction which requires significant amount of heat. And the process wise and also economic wise, it is an efficient method and which meets the demand of growing demand for energy. Then the technical aspects with respect to steam methane reforming method. So in this method, selecting a suitable catalyst is a prime factor. Mostly nickel-based catalyst or aluminum oxide are commonly used. And the heat input, as I mentioned, it is an endothermic reaction which requires external heat, which is often supplied by burning a portion of natural gas or any byproduct gases. And the reaction which converts methane and water into carbon monoxide and hydrogen, and this involves an additional step which is a water gas shift reaction. So the carbon monoxide produced is further reacted with steam in a second step to produce additional amount of hydrogen and carbon dioxide. So this occurs at lower temperatures around 200 to 450 degrees Celsius in the presence of a catalyst like iron, chromium or copper zinc catalyst. And this is the integration. I mean, this process is an integration with the carbon capture and storage can yield blue hydrogen. If this integration part, there is a carbon capture and storage, if it is exempted, then it produces a green hydrogen, which is around 9 to 10 kg of carbon dioxide per kg of hydrogen that is produced. And when it is combined, I mean, when it is integrated with the carbon capture and storage, the steam methane reforming process can produce blue hydrogen. Then the next method, partial oxidation. So partial oxidation is again another thermochemical process for hydrogen production, which is suitable for various kind of hydrocarbons, including natural gas, fuel oil, and coal. So the hydrocarbon feedstock, so that reacts with a limited amount of oxygen at high temperatures around 1000 to 1500 degrees Celsius at elevated pressure. And it is an exothermic reaction. So the reaction is methane with oxygen to produce carbon monoxide and hydrogen, and it is an exothermic reaction. The types of partial oxidation process are thermal partial oxidation process and catalytic partial oxidation process. Thermal partial oxidation process does not require any catalyst. It is a non-catalytic process, but which requires high temperature. Catalytic partial oxidation process, obviously, which requires a catalyst, most often platinum on aluminum oxide that's used, which operates at temperatures around 800 to 900 degrees Celsius. And this process is generally faster and requires small reactors, but they are sensitive to sulfur impurities. Then again, production of hydrogen, water electrolysis method. Water electrolysis is a process that uses electrical energy to produce uh, hydrogen. I mean, it uses electrical energy to split water into hydrogen and oxygen. So, when powered by renewable electricity, it produces green hydrogen with near zero greenhouse gas emissions. What is the principle involved in this water electrolysis method? It is a reverse of fuel cell operation. What happens in fuel cell operation? So in fuel cell process, hydrogen and oxygen combine to produce electricity and water. In this electrolysis, electricity is used to break down water to produce hydrogen and oxygen. So the overall reaction is water with the in the presence of electrical energy produces hydrogen and oxygen. I mean, water is split with the help of electrical energy into hydrogen and oxygen. It is an electrochemical process which involves the anode oxidation and the cathode reduction. Anode oxidation in the sense the water molecules loses electron to produce oxygen gas and also protons, which depends on the electrolyte used. Then cathode reduction, so that involves the protons or water molecules gain electrons in order to produce hydrogen gas. There are various types of electrolyzers used for this purpose. They are alkaline water electrolyzers, proton exchange membrane electrolyzers, solid oxide electrolyzers. What is it? Alkaline water electrolyzer. This uses an aqueous alkaline electrolyte like potassium hydroxide and typically operates at the temperature 70 to 100 degrees Celsius. But there are certain drawbacks in this process, like its lower current density and also a lower gas crossover. And proton exchange membrane electrolyzers. So it uses a solid polymer electrolyte membrane that conducts only protons. So this operates at lower temperatures around 50 to 80 degrees Celsius and at higher current densities with a good dynamic response, making this process suitable for coupling with intermittent renewable sources. And this requires, but the drawback, it's like it requires expensive catalysts like platinum group metal catalysts. Then solid oxide electrolyzers, which uses solid ceramic electrolyte and operates at high temperatures around 600 to 900 degrees Celsius. So this high temperature allows for use of steam, reducing electric energy input and increasing the efficiency. I mean, it increases the efficiency. Then the next method, direct thermal and thermochemical water splitting methods. So these methods use high temperature or a catalyst to split water directly without consuming electricity. Direct thermal water splitting. So the principle involves heating water to extremely high temperatures around or we can say more than 2500 degrees Celsius to dissociate water directly into hydrogen and oxygen. But the drawback is it is extremely high temperature process. So it is difficult, or we can say it, the material challenge involved in the reactor design. That is a major drawback in this process. The simultaneous production of hydrogen and oxygen at such high temperatures also presents a challenge in separating them to prevent recombination. And this method is largely, I mean, we can say it's not that much economically and also technically feasible. The other method, a thermochemical water splitting method. So this method utilizes some intermediate compounds to split water at much lower temperature, around like 500 to 2000 degrees Celsius, which is lower than a direct thermal water splitting method. So the intermediate chemicals can be regenerated and recycled within the closed loop, and that is the main advantage compared to direct thermal water splitting method. So what are all the intermediate chemicals that are used in this thermochemical process? So there are sulfur iodine hybrid sulfur cerium oxide. In case of sulfur iodine cycle, there are three steps of cycles involved: uh, sulfur trioxide, sulfur dioxide, and hydrogen iodide. This operates at temperatures around 850 degrees Celsius. Hybrid sulfur, so it is a two-step cycle where sulfur dioxide is oxidized to sulfuric acid electrochemically, and the sulfuric acid is then thermally decomposed to sulfur dioxide, oxygen, and water vapor. In cerium oxide cycle, a two-step metal oxide cycle using cerium oxide that requires very high temperature up to 1500 degrees Celsius for the reduction step. The advantages of this method are it is potentially high efficiency, high efficiency is involved, and it can be driven by high temperature renewable heat sources. And what are all the challenges involved in this? High temperature still poses some material challenges, and corrosive chemicals in some cycles, and also complex process integration. Next topic, fuel cell technology. Fuel cells are electrochemical devices that convert the chemical energy of a fuel, example hydrogen, natural gas, or methanol, and an oxidant directly into electrical energy through a controlled electrochemical reaction without any combustion reaction. So they are highly efficient and produce very low emissions. So what is the electrochemistry behind fuel cell operation? So the fuel cell consists of two electrodes. One is anode and cathode separated by an electrolyte. A catalyst, typically platinum for hydrogen fuel cell, is coated on the electrodes. So that anode oxidation uh, reaction that involves fuels that is supplied to anode where it undergoes oxidation, releasing electrons and ions. And under cathode, cathode reduction reaction happens An oxygen oxygen is supplied to the cathode where it reacts with the electrons and ions to form a product, typically water, and produces electrical energy with some heat. So the overall reaction is the combination of fuel and oxygen to form a product. So that is what here explained. So in the cathode reaction, so oxygen reacts with electrons and ions to form the product, that is water. So the overall reaction or the overall process that involves hydrogen and oxygen combine to initiate the reaction. Water is produced as a byproduct of the reaction. Electrical energy is generated as a primary output and heat is released as a secondary output of the reaction. So what is the thermodynamics involved in this fuel cell operation? So Gibbs free energy. Uh, so the maximum theoretical electrical work that can be extracted from fuel cell is given by change in Gibbs free energy at a constant temperature and pressure. So this W, so that denotes the theoretical electrical work, and that is equal to change in the Gibbs free energy. So this is equal to NFE, where N is number of moles of electrons transferred per mole of fuel. Then F refers Faraday's constant, and E is standard electromotive force. Then enthalpy entropy concept involved in that, the total energy released from the reaction, that is including electrical energy and also heat. The difference between heat of reaction and the electrical energy generated represents the heat generated by the fuel cell. Entropy involved in this, the change in entropy contributes to heat generated or absorbed. So the change in Gibbs free energy, that is equal to change in enthalpy minus T absolute temperature into change in entropy. So unlike heat engines, fuel cells are not limited by Carnot efficiency as they convert chemical energy directly. So the theoretical maximum efficiency of the fuel cell is determined by the ratio between change in Gibbs free energy and change in enthalpy. And the actual efficiency is lower due to irreversibilities that cause the actual operating voltage to be less than the electromotive force. So the actual efficiency is the ratio between actual electric work output by the total energy input in fuel. The fuel cell efficiency, so which is given by, which is represented by the ratio between actual electrical work output to the total energy input to fuel. So which is given by this expression. So with this we are completing the basic principle about fuel cell operation. Next, proton exchange membrane fuel cell. So what is a proton exchange membrane fuel cell? This is also known as polymer electrolyte membrane fuel cells, which are a type of fuel cell characterized by their solid polymer electrolyte membrane, which conducts protons. They operate at low temperatures and they have a high power density, making them more suitable for automotive and also portable applications. So that is what, as I mentioned, so this involves low temperature operation and also high power density and applications automotive and also portable applications. What are the components of proton exchange membrane? So the prime or the core components of proton exchange membrane fuel cell are proton exchange membrane, anode and cathode catalyst layers, gas diffusion layers, then bipolar plates. So this proton exchange membrane, it is a thin solid polymer film, for example Teflon, made of perfluorosulfonic acid, and that is permeable to protons but impermeable to gases like hydrogen and oxygen. So it acts as the electrolyte. The catalyst layers, there are anode and the cathode catalyst layers. So the anode catalyst layer, platinum based catalyst coated on a carbon support that is used where the hydrogen oxidation takes place. The cathode catalyst layer, which is a platinum based catalyst coated on a carbon support where oxygen reduction occurs. Then gas diffusion layers, porous carbon paper or a carbon cloth layer adjacent to the catalyst layer. So they provide electrical conductivity and allow gas diffusion to the catalyst and facilitate the water removal. In bipolar plates, graphite or metal plates with the engraved channels, they distribute the reactant gases to the gas diffusion layers, collect the current, provide structural support, and also manage heat and water. So, what are all the key steps involved in this proton exchange membrane fuel cell? The first one, hydrogen supply. So, gaseous hydrogen is fed into the anode flow field. That what reaction takes place? So, at the anode catalyst, hydrogen molecules split into protons and electrons. Then proton transport occurs. So, the protons pass through the proton exchange membrane to the cathode side. So the electrons cannot pass through the membrane, so they are forced to travel through an external circuit, generating electric current. Then oxygen supply. So oxygen is fed to cathode flow field. What reaction takes place in cathode? At the cathode catalyst, oxygen molecules react with the incoming electron and protons to form water molecules. Then water removal. So the water produced at the cathode is removed through the gas diffusion layers and flow channels. Operating temperature is around 60 to 80 degrees Celsius and the catalyst is platinum. Next topic, clean fuels. So what are the clean fuels? So clean fuels are energy sources that produce significantly less pollution, particularly greenhouse gas emissions and other pollutants compared to conventional fossil fuels when it is burned. So their use is central to achieve um, cleaner technologies and sustainable goal. So what are the various sources of clean fuels? So one by one, let us see hydrogen. So hydrogen is it is a versatile fuel. When it is burnt with oxygen, hydrogen produces only water, making it a zero emission fuel at the point of use. And the fuel cell electric fields, power generation, industrial feedstocks are certain areas of applications of hydrogen. Then biofuels, these are the fuels derived from biomass, like biodiesel, bioethanol, sustainable aviation fuel, biogas. Biofuel, the biodiesel, they are produced from vegetable oils or animal fats through trans esterification. It can be blended with petroleum diesel or it can be used directly in diesel engines that reduces particulate matter, carbon monoxide, and also greenhouse gas emissions compared to fossil fuels. In case of bioethanol, which is produced by fermenting biomass. It can be used as a blend with gasoline, and it reduces carbon monoxide and some hydrocarbon emissions. Then sustainable aviation fuel, which is again a biofuel, which is used as a jet fuels that meet specific sustainability criteria, and it can significantly reduce greenhouse gas emissions for aviation purpose. Then biogas, produced from anaerobic digestion of organic waste, and biogas is a mixture of methane and carbon dioxide upgrading to biomethane, which removes carbon dioxide and also other impurities. Then natural gas. Uh, like natural gas is considered a clean uh, fuel than coal and also fuel oils, as it produces lower carbon dioxide and sulfur oxides and also particulate matter. It is a critical bridge fuel in energy transition, and there are various applications of natural gas like power generation, industrial heating, residential heating, and also transportation, electric power. Again, one more source of clean fuel. I mean, the produced from renewable sources. Then ammonia. It is a it is gaining attention as a carbon-free fuel and a hydrogen carrier. It can be produced from green hydrogen and nitrogen. There are various advantages of ammonia: high energy density than liquid hydrogen, and also it is easier to store and transport. And but there are certain challenges like nitrogen oxide emissions during combustion, and also there's some toxicity involved in that. So with this, I'm completing module 3. Thank you all for listening. Thank you.